Hi everyone, I hope we're all doing well this week. Welcome to my final project presentation. I hope you all enjoy it, and if there are any questions, please don't hesitate to reach out through the discussion boards. We'll start by introducing the topic and study area for the project, then we'll discuss some important characteristics of the data that went into developing the final map product, followed by another discussion where we'll explore the methods and processes required to create the final product. We'll wrap up our discussion with an overview of the results of the analysis and a presentation of the final map product. I focused my final project on storm surge modeling and how these models can influence emergency management. For my final map product, I chose to analyze environmental data and create storm surge layers. I chose this topic because the implications of this technology, whether I like it or not, have played and will surely continue to play an integral role in my life and future well-being. A storm surge is a statistically significant rise in sea level resulting from a combination of three storm conditions: low atmospheric pressure, strong fast winds, and land-trapped waves. More plainly, a storm surge is what happens when hurricane-force winds trap seawater close to the shoreline, and after a certain pressure threshold, the seawater rushes inland and the coastline recedes dramatically. Without appropriate protocols in place to prevent disaster and enforce evacuations, coastal and inland communities risk major flooding, infrastructural damage, and in some cases, loss of community members. I focused my final map product on the Florida Peninsula with special focus on the Tampa Bay area. The study area exists in the North American subtropics and extends towards the equator, creating a peninsular shape that makes Florida uniquely susceptible to hurricanes and storm surges. In fact, the combination of location and geomorphology makes the state of Florida have one of the highest counts of hurricane frequency in the country. The peninsular shape and low elevation easily trap storms along the shoreline. Folks living around the Tampa Bay area experienced such a strong storm surge during Hurricane Ian that almost all of the water in the bay was moved inland and didn't return until a few days after the storm had passed. In fact, Hurricane Ian was named the third most dangerous hurricane in U.S. history in terms of impacts to infrastructure and the environment. It was such a surreal experience that I couldn't help but want to explore it through this project. While my final map product does cover the entire state of Florida, the Tampa Bay area is featured as a particularly vulnerable area to storm surges. The long, flat bay has low surface relief, so seawater is able to surge easily and quickly. Virtually all of the data used for this project originally came from government entities at the federal, state, regional, and local levels and can be accessed either through the ESRI ArcGIS online portal or the original source itself. For example, I needed elevation data to create a storm surge layer and chose ESRI's terrain imagery layer as the basis for my analysis. This was to ensure validity of the data and reduce the margin of error. Precipitation data for Hurricane Ian's landfall on September 28, 2022 was sourced directly from NOAA and the National Weather Service's joint AHPS Precipitation Analysis Portal. To capture natural imagery of the featured area, or the Tampa Bay area, I pulled 3 Landsat 8 data files from the USGS Earth Explorer portal. These Landsat images were captured during the week leading up to Hurricane Ian's landfall, between September 20th and September 27th, with a maximum of 10% cloud cover. These were all raster data files. Finally, I looked to the ESRI ArcGIS online portal for data to highlight my areas of interest. I found another raster file of natural imagery covering Florida's southwest coast immediately following the storm, capturing surge inundation. This was from a member of NOAA, whose username is presented on the slide. Vector shapefiles for the state of Florida and city of Tampa boundaries were found the same way from the Southwest Florida Water Management District and the city of Tampa's public information accounts, respectively. I organized my methods into 5 distinct, easy steps to make it more digestible. First, I loaded all the data onto ArcGIS Pro. Then, I manipulated and analyzed individual layers to create new information. The next step was to assemble the loaded data and newly created information into individual maps. The final step was to complete the cartographic layout of the map. The first step of my analysis was to compile and organize my data in my hard drive and load it to ArcGIS Pro. Initial data uploads included the terrain layer, Landsat 8 imagery layers, and a precipitation imagery layer from the day Hurricane Ian made landfall in Florida. I followed a simple workflow to modify the data. To prepare my elevation data for analysis, I exported the original terrain layer using the map extent of my Florida boundary shapefile. I then clipped the new terrain layer to fit my Florida boundary geometry, thus rendering a terrain layer for the state of Florida. I then applied a remap function to apply a z-factor of 0.00001036 which is appropriate for locations around the 30-degree latitude according to Esri. Preparing the Landsat data required an extra step. First, I used the merge rasters raster function to create a new raster imagery layer containing all three quadrants. I then clipped the result of the merge to the Florida boundary geometry, providing me a rendering of natural imagery of the Tampa Bay area in southwest Florida, the areas most impacted by Hurricane Ian storm surge. Preparing the precipitation data followed a similar workflow. I simply clipped the original layer to the Florida boundary shapefile to give me a clearer image of how much precipitation fell during the event in Florida. The primary analysis aimed to create my storm surge layer using my remapped weighted elevation raster layer. I used the con function to create a binary output that would highlight areas exceeding a certain storm surge depth threshold. Here I applied an average 5-foot inundation level using the expression value is less than or equal to 5. This created an output layer with two classes, one with values less than or equal to 5 feet, valued at 0, and another with values greater than 5, valued at 1. The result was a delineated 5-foot storm surge zone established throughout Florida. I applied the same analysis to create 12-foot and 18-foot inundation depth layers. These were the lower and upper limits of the storm surge depth range that occurred within the Tampa Bay area, respectively, due to Hurricane Ian. The results of my storm surge analysis tell me that Florida simply cannot handle large-scale surges. Even at a 5-foot inundation depth statewide, almost a third of the peninsula is underwater. The 12-foot inundation seems to affect low elevation surfaces more, while the 18-foot inundation floods half the peninsula and causes major waterways to swell and overflow. These results indicate that the state of Florida should consider establishing flood-resistant infrastructure to minimize physical damage while implementing statewide emergency management protocols to safeguard communities. Applying the con function was the method that worked best for me. However, it is not a comprehensive analysis compared to the hydrology raster toolbox. If I were to replicate this process with ample resources, I would establish a workflow that uses the same original data as well as land cover data, but would apply a string of hydrologic functions to establish fill, flow direction, flow accumulation, distance to shore or boundary shapefile geometry, stream order, and finally a flood risk layer. However, the necessary inputs required resources, skills, and knowledge that were outside my reach at this time. Here's my final map product. It's a dual layout showing Hurricane Ian's path across the Florida peninsula, as well as the location of the city of Tampa. The map on the left contains a raster of precipitation data from Ian's landfall on September 28, 2022, with a 5-foot storm surge superimposed. The map on the right shows flood inundation at 12-foot depths and 18-foot depths, the exact range experienced in the Tampa Bay area, superimposed over natural imagery of the area to highlight the amount of land, property, etc. lost to such a surge. It already happened once that we know of, and an exacerbated climate change will only increase the risk of these surges happening again in the near future. One takeaway should be that a, quote, perfect storm of conditions is not necessary to experience a dangerous surge. In the map on the left, the high volume of precipitation in the southern portion of the peninsula and lack of such precipitation in the Tampa Bay area indicates that rainfall was not a major factor in developing the surge that occurred there. A final takeaway from this should be that the state of Florida needs to consider surge-resistant infrastructure and emergency management protocols to mitigate the devastation. Thank you.